All right. Good morning, everyone. Or once again, it's morning where I am. Hello, Emmanuel. Hello, Mohammed. Hello, Kiwana. Hello, Tolo Lope. Hello, Tolo Walona. Hello, Aber. Hope you're all doing well this morning. Sorry, I keep on saying morning because it's morning where I am. Force of habit. Hello, Vishal. Hello, Kwame. Hello, Akshay. Hello, Dewita. Hello, Johnson. Hello, Oleya. Hello, Yanis. Hello, Alka. Hello, Afungchui. I hope I'm saying your name correctly. Hello, Dennis. Hello, Danielle. Buenos dias from Mexico. Hello, Alexander. Hello, Naga. Hello, Hendry. I thought I would begin here by kind of finishing off this sieve function, and then we could talk about other things that you guys want to talk about. I mentioned the Sieve of Eratosthenes, which is this procedure for identifying prime numbers. Right, the Sieve of Eratosthenes. So said here, in principle it's a faster method for finding primes, but you need more memory because you basically start out by making this big list of numbers. And then, essentially crossing numbers out. So, I described this yesterday. Right, as I said, we basically write down a list of numbers and then we more or less go through crossing out numbers in a particular pattern, right? We'll cross out 0 and 1 because they're not prime. We'll start with 2 and then we cross out all the positive multiples of 2. Hello, Uluk. And then we cross out 4, 6, 8, 10, and 12, and 14 and 16, and so on, however high we go up to. 3 is the smallest number that remains that's not circled nor crossed out. So 3 is a prime number, and then we cross out 6, and 9, and 12, and 15, and 18, and all the multiples of 3, up to the point that we care about. And then the next number that remains, which is neither crossed out nor circled, at that point would be 5. And then we'd cross out all the multiples of 5, the higher multiples of 5, and so on. When we're done, we're left with a set of prime numbers up to the point where we stopped writing our list. And we just wanted to implement a few functions which will help us do this kind of thing, do this kind of procedure. So, said we generate a list of all the numbers between 0 and n inclusive. Mark the numbers 0 and 1 to be not prime. And then starting with p is 2, mark all numbers of the form n times p, where n is strictly bigger than 1 and n times p is less than or equal to this capital N. To be not prime, because these are all multiples of 2. Find the smallest number greater than p, which is not marked, and set that to equal to p. Go back to step 2. Stop if there's no unmarked number greater than p and less than n plus 1. Right, so this is the idea. As I said, our general strategy, as I said, to use the Python list. The index of the list will represent the numbers. And so, so we don't make a list of the numbers. Well, we're going to represent this list as a list of true and false. Right, false being this number is not a prime, true being this number could be a prime. And when we're done with this procedure, all the ones which are marked true are the prime numbers up to the point that we have checked. Up to this endpoint. So, I said some functions we're going to make. So this list true, we did this yesterday. Make a list of true values of length n plus 1 where the first two values are actually false. Yeah, we could get to talking about classes later in this office hour. I know that's part of this week's notebooks or the videos and the notebooks are talking about classes. We'll have a mark false method which takes a list of booleans and a number p and mark all the elements at indices 2p, 3p, etc. false. As I said, this corresponds to step 2. The find next said find the smallest true element in a list which is greater than some index p, i.e. has index greater than p. Said this gives us our step 3 in this algorithm. And then, this prime from list return indices of true values. So I mentioned yesterday, here's, say, 2 ways that we could create this list true n function. So we start with a list of true false values, and then we create this list of trues for the appropriate numbers, and then we concatenate these two lists together, right? Remember, the plus between two lists is list concatenation. Or I said, well, here is another way that we could get the same result. Right? We'll just have a Boolean test. So we range from I starting at 0 up to and including n. This is what the range n plus 1 here does. And then we check, is this number I greater than or equal to 2? Well, when I is 0, this will be false. When I is 1, this will be false. When I is 2, this will be true, and then I is 3, this will be true, and so on, and so we end up with this result right here. Right, so 2 ways that we could end up with the same result. So there's this list true function here, which basically initializes this list in the format that we want. So this is saying 0 is not a prime number, 1 is not a prime number. The rest of these numbers could be prime numbers. This is what we mean at the moment, right? Because this is how we are initializing this list. And then there's this next function, this one that was being called mark false. We want to take a list of elements, a list of these true false values, like the one that we've generated from list true, and a number p and marks elements false which are in the range 2p, 3p, 4p, etc. So the function that I mentioned yesterday as well, here's our Boolean list. Here's our number p. And so we want to start at 2p, go up to the end of the list, and we want to advance our index, our value I by p. So I'm going to start when I is 2p, then the next value of I will be 3p, and then we add p again, we get 4p, 5p, etc. And of course there are various ways of getting the same possible values for I. This is just one way. Well, start with 2p and then advance this value by p every time. All right, just add p. We set these values equal to false because we're saying, all right, these values are not prime numbers because they are positive. They are multiples of p larger than 1, right? 2, 3p, 3p, etc. So this gives us our step in this Sieve of Eratosthenes. Well, the idea, so DeWitt asked a question, why 2p? Well, remember, the idea is that this number p we're thinking right here is a prime number. And we want to mark, like if p is 2, we're going to mark 4 and 6 and 8 and so on as being not prime numbers. But 2 is still a prime number. If p was a prime number like 3, well, we want to mark 6 and 9 and 12 and so on as being not prime. So we want to start with 2 times p if we're thinking p is a prime number. And here we're checking, right? We started with our initial list for the numbers from 0 up to 6, including 6. And we want to mark, we want to run this function when p is 2. So we want to mark the indices 4 and 6 as being false. So 0, 1, 2, 3, 4 we've marked as false. 6 we've marked as false. Any other questions about what we're doing here so far? All right, we're trying to implement these steps of this Sieve of Eratosthenes. So we have a function which will initialize this list of true and false values. We have a function here which will do what it says, take a list of booleans and a number p, mark all elements 2p, 3p, 4p, etc. false. And then we want this find the smallest true element in a list which is greater than some value p. Right, I need to add in this greater than some value p because, well, right, it's this kind of procedure that, like the first time through here, we've identified 2 as prime. I want to find the next number bigger than 2, which hasn't been marked as not being prime. I can't start from the beginning because, well, I'd always just get 2. I need to start at some point and look for the next value, which the smallest true value, which is greater than some index, right? Has index greater than p. As I said, this will allow us to do step 3 of this algorithm. So let's pause for a moment here and consider or remind ourselves of the enumerate function. Size asks the question, this method is only faster if you want to get a collection of primes, not if you want to figure out if a certain number is prime. Yes, that's more or less true, yeah. Yeah, this is for a whole collection of finding a whole collection of prime numbers, or finding all the prime numbers up to some point. Yeah, if you want to figure out if a certain number is prime, there are other quicker ways of doing this. So the find next function, so right, we're given a Boolean list and we start from some index p, or we basically want to start from index p plus 1. Right, I want to go from the first element after index p. Why am I mentioning this enumerate function? Well, is because we can use this for I in enumerate. Let's look at some lists, 21, 34, 10, and 12. Sorry, for index an element, the enumerate actually gives us tuples. So enumerate is a useful function when we have to iterate over a list, and for example we might be interested in the index and the value in the list itself. Right, enumerate, well, starts from the beginning of the list by default. Hannibal, yes, as I said, you could do this mark false in other ways. And that will give the same result. Right, you just need some way of picking out the multiples of p starting from, 2p. Yes, Hannibal, you could do it exactly the way you did it there. I personally might think that this is slightly easier to read because, well, I could see kind of immediately, well, I start from 2p and I'm incrementing by values of p. While your method will work to give the same result, well, I have to read and interpret a bit more to figure out that you are changing the increments of p starting from 2p, and you're incrementing by p. Right? I just think, to me, this is slightly easier for me to read this code and interpret what's going on in the code. But both methods will work. Let me put this list here instead, because we could examine how I could change the use of this enumerate function. So if I make this list, I could like start my enumerate from I could enumerate over a portion of this list. I slice, say, the final 3 elements from this list. But what I might want to do in that case then is to start where, specify where my enumerate starts from, where this index starts from. If I start from index 1, well, why not specify index 1 right here? Because, well, then this index 1 matches up with this index here. Right, the idea here is, well, I could use this enumerate in this kind of fashion here to look at my portion of the Boolean list. Because I could say for index and element in enumerate bool list. I'm going to start from position p+1. And I'm going to start my indexing from position p+1. If element return index. Otherwise, I'll return none. Right, remember this element right here is going to be a true or false value. So I could just check, is this element true? Find next. Oh, well, I have some asserts right here. Find, let me copy this here. Find next. So I started index 2, 0, 1, 2. Well, I'm looking for the next index, if there is one, after index 2 that has the value true. Oops. Find the next. Well, this doesn't print out anything because, well, again, none doesn't get printed out unless I explicitly tell it to print out. Right, but the idea here, again, I'm going to start at position p+1 in my list, because, right, I want to check starting after index p. Right, and the enumerate right here gives me tuples. It gives me an index, or it gives me a number, which I'm calling index, and it gives me an element from this list. my index right here is starting from position p plus 1, right? So index, the first value of index right here is going to be equal to p plus 1. Why am I doing this here? Well, again, because I want this index to match the index I'm actually looking at in my original list. Right, I could just say, well, for example, for testing purposes, if I print out these elements, right, if I, let's say if I put this to be, false, if I were to, if I change this, say, to false, and I start from index 1, or if I turn this to be true, well, remember, I want to start. So Ulrich asked the question, why p plus 1? Do you mean this part here, Ulrich? Well, because I want the index right here to match up with the index in my original list. If I remove this, my index right here is going to start from 0. But here I'm actually, I'm beginning here. It's going to return 1, but I want this number right here to match up with the index in the original list. Otherwise, it's going to start numbering from 0. Right, again, if I look at the enumerate help string, excuse me, my default starting point in enumerate is 0. But in general, I'm not starting, I want the index right here to match up with the index in the original list that I started with. And I want to start with index p plus 1. So now, given a list of true and false, return the index of the true values. So, right, if I were to give a list of trues and falses, I want to return the indices for the values which are true. Well, here again, this is if I could use enumerate again. I want index for index element in enumerate Boolean list if element. So, right, like for example, again, if I take this as an example, prime from list, we just iterate over, so 0's false, 1's false, index 2 is true, so I keep index 2. Index 3 is true, so I keep index 3. Index 4 is false, I don't keep it. And, well, my Sieve function right here has been conveniently written for me, like assuming that my list true function works correctly. My mark false function works correctly, my find next function works correctly, and my prime from list function works correctly, well, this is my sieve of Eratosthenes. Let's try this out. Sieve of 10. So I want all the prime numbers less than or equal to 10. I get 2, 3, 5, and 7. If I change this to 11, well, I get 11 because 11 is a prime number. If I go up to 12, well, I get the same list as I had at 11. If I go to 30, well, I get all the prime numbers less than or equal to 30. We could check, my sieve function here. Is it the same as do I get the same results as my sieve, as my get primes? Yes. We could compare this, my sieve function and my get primes function. Which one is quicker? Microseconds and milliseconds. Well, micro is smaller. Milliseconds is what, 10 to the minus 3? Microseconds here, so 701 microseconds in cell number 98, right? 701 microseconds. Micro is what, 10 to the power minus 6. Milliseconds here is what, 10 to the power minus 3. So my sieve function is quicker. If I bump this up by going up to 10,000, my sieve function is what, 10 times faster than my get primes method. And this sieve function right here that was provided for us, well, the grader can check this, right? But we're really checking is the list true function correct? And is the mark false function correct? And find next correct? And prime from, right? It's all these things. So remember, when we give a function name to the grader, the grader runs this function on some hidden test cases and checks to make sure that the function works correctly on all of those hidden test cases. So it's not just, it's not just checking like, 1,000 or something. There's several test cases that it's running. As I said, this Sieve of Eratosthenes is, it's a rather classical method to generate prime numbers. It's still not going to be very efficient, to generate the large prime numbers that we know about these days. The prime numbers with millions of digits. So is there any question about anything that I've done here for this problem? Oops, apologies. Sorry, I had some brief message elsewhere, and I completely forgot I was on camera for a moment. Apologies. So we've talked about the VC Mini project. Well, we might need to talk about classes a bit more generally first. So objects, objects in Python are important. Basically, in case you don't know it, everything in Python is implemented as an object, from the simplest integer to the Boolean and so on. Does the grader also check for a certain amount of minimum compute time of your function? No. We're just checking if your functions are correct, if they give the correct answers. What is the order of the notebooks containing data wrangling notes? Let me see if I could find week 3. Well, notebooks for next week are the Pythonic notebook, the PY Pythonic notebook, PY Pythonic, which I think should finish off the notebooks in the Python subfolder. And then data wrangling. We have, we begin with the IO notebook. After that, in week 4, we have IO and then the basic DS modules. And then after that, we have pandas, intro statistics, and then data munging, and then SQL. And finally, the classes in ORM. But essentially, as I said, to begin with, you start out with DSIO, and then the basic DS modules. So classes in Python, as I said, everything in Python is, an object. From the kind of simplest Boolean data type and ints and floating point numbers and so on. So, understanding these principles of object-oriented programming, even if you maybe never want to write your own class, it's still useful to understand, on some level, what's going on behind the scenes. Because, right, an object has methods. In this OOP notebook right here, right, we mentioned some of the ways that you could inspect an object. A dictionary is a class in Python. We create instances of the dict class when we create new dictionaries. So, in this example, in this notebook right here, we go through this kind of example here of creating a new class for rational numbers, dealing with fractions. Now, as we mentioned right here, typically every class, if you're storing anything inside a class, right, you're going to need an init method. or if you're storing some, sorry, well, I should rephrase. I should be more careful with my choice of words. If I want to create a class and pass information to the class when I create it, then I want my class to have an init method. Right? When this class, when the instance of this class is created, the init method is automatically called for us. Right? We don't have to do that ourselves. The init method right here is called for us. So can I repeat about the init method? So as I said, if we want to pass information to an instance of our class when we create the instance, then we want our class to have an init method. Because once again, you know, the init method is called for us automatically when we create an instance of the class. There are lots of special methods and classes. Here we're referring to these as hidden methods. And these sort of hidden methods, they begin and end with a double underscore. A double underscore, sometimes referred to as a dunder. You know, D-U-N-D-E-R, dunder, double underscore. So, yeah, Vishal uses the word constructor. We can think of this method right here as a constructor for the class. What is self? Well, this is described a little bit here. Both of the methods took as a first argument the keyword self. They said, what is the function? Yeah, the first argument to any method in a class is the instance of the class upon which the method is being called. Think of the class like a blueprint from which many possible objects are built. The self argument is the mechanism Python uses so the method can know which instance of the class is being called upon. Right, so when this method is called, I like to use the word kind of pointer. The self right here is kind of a pointer to the instance of the class itself. And you know, yeah, this is necessary, right? And all of your method definitions in a class, we need this first argument. Now, there's nothing special about the word self. It's just this is the conventional word which is used in Python, right? This is a signal to me, the programmer, and other programmers that, you know, this is an object. And again, well, you know, we use the word self as the conventional name. Well, the Alka, the init method you're defining here is the user-defined constructor. So this is the constructor that we are defining as the programmer. Unlike other programming languages, some programming languages, a class could have more than one constructor. That's not the case in Python. Like other classes, you might have constructors which have different numbers. No, you can't have a different name. I mean, the init method might call another function inside it. But no, this is the name that you need to use if you're going to define your constructor, your init method. These hidden method names are very special. You can't change them. Another special hidden method name is this one, the double underscore REPR, the double underscore. And that's the repr method, usually it's referred to. So yes, you can only have one constructor in Python. One constructor per class. Now, the repr method is what gets called. It's, the interpreter, the Python interpreter behind the scenes is doing a lot of work that we normally don't notice and don't have to notice. When we create an instance of this rational class, so we could define the class, we could create an instance of the rational class. If we call the print function, what's actually happening is that the Python interpreter looks around and says, oh, is there a repr method which is defined on this class? And if there's a repr method defined on this class, this string right here, the repr method should return a string. The repr method is what you see when you print an instance of the class. Agile, there's lots of special functions that begin and end with a double underscore. Not every double underscore corresponds to some sort of special method. I mean any, because of course I can make any name. But yeah, essentially there are lots of special methods which are used in various ways. Like I said, when I say print on an instance of a class, the Python interpreter says, "Ooh, does this class have a repr method?" And what you see when you make a call to the print function is what the string that the repr method returns. The repr method should always return a string. There's nothing that enforces that. It's just that is what the repr method should return. So yeah, you could kind of say, this is, the repr method is like a display function. This is what you see. This is, I think of REPR as short for representation. Right? This is the representation that you are giving to an instance of this object. And so when I print out an instance of this instance of this object, well, this is what I see right here, because this is the way the repr method has been defined. So yeah, the repr method should return a single string. Nope, the repr method should be a single string. However that string is constructed is up to you, or is up to us as the programmer. But it should return a single string. And, right, other classes, right, you could, right, here we have an init method, and we could define some method. And that method could more or less do whatever we want it to do. Right, this doIt method will, print out the value of this variable which is saved in the class. Can you implement a class without explicitly defining the init method? Yes. That is possible. And then, like, this example right here, right, we define this kind of helper method. And this reduce method right here, calls this helper method. We're going to talk a little bit about a class variable and an instance variable. So to me, these may have different meanings, different definitions. So, to me, this is a class, this is how I can define a class variable right here. Right, this is a variable which is stored inside the class. I don't believe you have to mention this object here, but it's kind of conventional. I think the same will work if you don't explicitly mention this, and it will still work correctly. If you are inheriting from another class, then you will need to mention that other class here that you're inheriting from. Sorry, let me address Hannibal's question. So there's the repr method and there's the str method, the _str method. They're not quite the same thing. Let me see if I could remember. Data, Python data class. No, Python data model. That's what I'm looking for. So, I mean, if you look at the, sorry, I'm trying to do something. str. So sorry, the str method and the repr method, they have slightly different uses. To me, usually I will define the repr method and I will have the str method return the same thing. But, if you look at the explanations here, they say the repr method is built-in function to compute the official string representation of an object. Here they're saying, if at all possible, this should look like a valid Python expression that could be used to recreate an object with the same value. If not possible, a string of the form, some useful description should be returned. The return value must be a string object. Here the str method, it says called by, if you say str with an object and the built-in functions, the format and print to compute the informal or nicely printable string representation of an object. The return value again must be a string. So, you know, they have these different explanations here. As I said, usually I will make repr and string return the exact same string. But, you know, strictly speaking, they don't have to. You know, the str method is actually the one that's called by the print function. Basically, the Python interpreter will check on printing out an instance of this object. Is there an str method defined? Yes. If yes, it will use that. If there's not an str method defined, but there's a repr method defined, then it will use the repr method to print out, you know, the representation. So they aren't quite the same thing. You can define both, and they can be different. But usually, as I said, usually I might define the repr and the str method where they, you know, might return the same thing. But maybe that's not quite following good Python programming conventions. It says this, if at all possible, the repr method, this should look like a valid Python expression that could be used to recreate an object with the same value. So maybe what we might want to do here is let's copy and if I follow the Python conventions, what I might want to do is define this method to be the str method and return, and the repr method I might return something like this, right? The idea being is that this would be a string right here which I could use to recreate an instance of the object. So if I were to call fraction.repr, right, I would get, you know, this is how I could recreate the instance of this object as the repr method. But the string method right here, right, if I want to print this thing out, well, I can get this kind of nice representation as this fraction. So again, I can define both. The str method is what is used. If I say str fraction, then I get the string returned by the str function. If I call print, it calls this function right here, and I get that as the output. If I called repr on fraction, well, I get the string returned by the repr method of the object. Abstract classes and abstract properties. There's not quite a idea of abstract classes similar to how they are in Java, for example, where, you know, you define a class and it has abstract methods. There isn't quite such a thing in Python. You could define a class and you could define some methods where they return a not implemented method or a not implemented kind of exception. But you don't have abstract classes in the sense that, oh, if you try to create an instance of this abstract class, that's an error in other programming languages. You don't have that in Python. Yusuf asked a question, can we use a class to call a method without creating the instance of that class? Yes. You could define static methods in classes. Yeah, like static methods in Java. Yes, you could do that by using decorators to say this class is, or this method is static. So we could continue talking tomorrow about classes, and probably tomorrow, get into the VC mini project. Right, you want to define an init method and a repr method for this class. And then we want to start defining methods to use our classes in, arithmetic kinds of operations, right? All right, so Alka, you're saying there are abstract classes in Python. I might have seen this before, but obviously I don't remember. So between now and tomorrow, I shall try to have a look to remind myself here. I'm going to end things here for today as we're out of time, and we'll see you tomorrow at office hours. Thanks for the questions and the discussion, and we'll see you tomorrow.